this unit, we're going to discuss the nature of matter and atoms and start to understand why the periodic table is organized the way it is. So the first thing we're going to start with is a fellow by the name of Dmitri Mendeleev. Now, he is often called the father of the periodic table. The really interesting aspect of his organization of the periodic table is that at the time of his creating his table, there were about 56 or 60 elements that had been discovered. Now we have 118. But the really important aspect is that he recognized that certain elements share certain properties together. And he started putting these into different columns and different rows, and he recognized that maybe all of the elements had not been discovered yet. So he made a table with blank spaces. And this was very revolutionary for the idea. Everyone at the time had kind of assumed that most, if not all, of the known elements had been discovered, and he was not taken very seriously for his work. But he went forward with his research and had a lot of scientific data to back it up, with his showing how different elements and certain types of elements would combine, had similar properties, etc., etc. To his credit, in his lifetime, there were about 4 or so elements that were discovered that fit into his table with blank spaces. So we've actually come to recognize his table as being the first periodic table. And while there have been a few additions and changes here and there over the years, his table was not far off of the type of table that we use today, which is pretty amazing since he only had about 60 elements at the time to work with. His table and subsequent tables established what was known as periodic law. Now, this is why it's called the periodic table. The periodic law is when the elements display a regular and repeating pattern. And that is what the periodic table does. Every single row is called a period because every single row has the exact same trends. We'll talk more about this as time goes on, but all of the atoms, as you go across the periodic table, they get smaller. Masses tend to increase. The atomic number increases. Their reactivity changes. But every single row repeats the same pattern. It does the same thing over and over again. The next person I want to talk about is Henry Moseley. Henry Moseley is credited with discovering the atomic number. Now, the atomic number, it represents the number of protons. And while he did not discover the proton, he is the first person to mathematically figure out how to measure the atomic number. He used actually X-ray diffractions to be able to conclusively show that however many protons an atom has, that is its atomic number, and that is now how we define an element. That is now how we define an atom. Okay. Next thing I want to talk about are the groups, the up and down columns. These are also sometimes referred to as families. Okay, so the vertical columns they are similar, they are families because they have the same chemical behaviors. And what I mean by that, if I were to take a look at this first column here, lithium, sodium, potassium, they're in the same family because they all react the same way. Lithium reacts very, very violently to water. Well, so does sodium and so does potassium. They all tend to react the exact same way. Okay, likewise with beryllium, magnesium, calcium, and boron, aluminum, gallium. They all tend to react the exact same way, and that's why we group them into these families. Their chemical properties are what help define that. Okay, so next we'll talk about the horizontal, the periods, and as I said, the periods are the rows with a repeating pattern. Okay, every row does the exact same thing. The atomic radius does the same thing with each row, and the electron energies do the same thing with each row that we call electronegativities. And those are things we'll talk later on in the course. But every row will do the exact same trend, whether it be increase or decrease. It does the same trend. Okay. The next thing I want to talk about in the periodic table are metals. Now, as you glance around the periodic table, I hope that you can pick out some of the metals that you've seen before. Specifically, some like, nickel and silver and gold. Hopefully you know what mercury is. Okay, iron, magnesium. Okay, the really incredible thing about the periodic table is that most of the periodic table are metal. Actually, everything left of this little staircase over here is considered a metal. Okay, so left of the staircase is where the metals are located. Okay, now the other really unique thing about the periodic table is that every time you look at it, you've seen it drawn like this. The actual shape of the periodic table is something like this. You see, this box down here actually fits into the middle of the table right here. So we squeeze it in between these two sections. All right. The reason why we draw it like this is so that it fits nicely on a piece of paper. But it's very important that you understand that this section here actually goes into the middle of the table. And so now if you look at everything left of the staircase, that really does make up most of the periodic table. Okay. Some of the properties of metals. Okay, most of our metals are shiny. Most of them are malleable. Okay, you know your typical properties of metals. And for the most part, most of our metals on the periodic table are silver. Okay, with a few notable exceptions, copper and gold, but most of our metals are silver. Okay, so while it might actually take a trained eye to distinguish one metal from another, right? The next thing we'll talk about are the nonmetals, and for our purposes, those are going to be our gases. Okay, they are to the right of the staircase. Okay, gases. All right. A nonmetal is typically, it is typically a gas. Okay. We use some gases as insulators in computer server rooms, things like that. Okay. The next thing we'll talk about are metalloids. And metalloids are a generic term that we give to elements that have properties of both metals and nonmetals. Okay, and they tend to touch the staircase. Okay, so things like carbon. Carbon actually can conduct electricity, but if you think about carbon, like your pencil lead, it's very brittle. It'll break really easily. It doesn't stretch. It doesn't. You can't pound it into wires. Okay. Let's see, silicon. I'm sure that you've heard the term Silicon Valley. That is because we use that element in electronics. It allows electricity to flow without getting too hot like some of our other types of metals. So it is a great use in the computer industry. Okay, so these metalloids, they have properties of both. They don't have all the properties of both. Some might be brittle, some might be malleable, some might conduct electricity, some might not, and they tend to hang out right there along the staircase. Okay. I want to talk about the names of the families. So the first thing we're going to talk about are the alkali metals. This is group 1, the first column. Okay. Even though they are metals, they are very soft. Okay. You can take a piece of sodium right here and you can pull it apart. It's that soft. You can pull it apart with your bare hands, or you can cut it with a knife. Okay. They are also extremely reactive. If you ever do have sodium, you don't want to touch it with your bare hands because it will react with the oil and your skin. As soon as it touches air, it starts to oxidize and it starts to change and turn white. And if it's put in water and there's enough of it, it'll generate enough gas and it can actually blow up. So it's very, very reactive. The only way that we can keep it safely is if it's stored in like mineral oil, because it won't react to that. Okay. But some of the uses for these, hopefully you've heard of lithium-ion batteries. Okay. You've heard of sodium, probably in a different form. Some people, you refer to how much sodium is in food or in a drink, but that's actually talking about a compound called sodium chloride. But the metal sodium is part of that compound. Okay. The next group I want to talk about, group 2, are the alkaline earths. Okay. The alkaline earths, they are more dense, and they are stronger, but they are still reactive. And they are called the alkaline earths because they will create basic solutions. Okay, an alkaline solution is going to be a basic solution. So their solutions will have a pH of greater than 7. Okay, basic. Some of the uses of these, you find calcium in bones, or they can be used in X-ray machines, or even in Tums or Rolaids. Okay, so these are some of the uses you might see for those. The next ones I want to talk about are the transition metals, and this refers to groups 3 through 12. Okay, they're not extremely reactive, meaning they will be by themselves more often than not. You can find gold by itself and silver by itself. You can also find it bound to other things, and you can separate them a lot easier. Um, but they are relatively stable and not very reactive. Um, the number of electrons that these elements have in their outer shell can vary, okay, and you can have different types of transition metals, and we'll talk more about that as the year goes on. But you can have things like iron 2 and iron 3, and that has to do with how many electrons are out in their outermost shell. So we can have varying levels of transition elements, and you can find these in all kinds of different substances, especially in modern society and modern technology. All right. The next group we'll talk about is the boron group. It's a very ingenious name there. This is group 13. They have relatively low densities. And but they will combine with other elements. Obviously, aluminum foil is something that can stand on its own. We use aluminum foil daily, or at least some people do. If you like to cook, you might use it daily. But they can combine with other elements, okay? Aluminum is one of the most abundant elements in our crust, okay? So it is very stable, all right? Next group we're going to talk about is the carbon group, group 14. This consists of metals and non-metals. Silicon being the second most abundant element in our crust, okay, which again, that's good for technology's sake, because that means that we have a lot of it, and it's readily available, especially in today's age with cell phones and computers and tablets and even computers in cars, etc., etc. So it's widely used, all right? But the carbon group has lots of varied properties, because you're talking about metals and non-metals and metalloids, and each one of them kind of does its own thing, okay? Nitrogen group, next. Again, we've got metals and non-metals and metalloids. Nitrogen being one of the most abundant elements on Earth, because 79% of our atmosphere is nitrogen gas, okay? So it's readily available. Nitrogen can be pumped out of just normal air and filtered out relatively easily, okay? But again, these are varied properties just because we have gases all the way down to metals, all right? Excuse me. Let's see, let's look at, let me write that down, nitrogen, about 79% of the atmosphere. Okay, the next is our oxygen group. Okay, group 16. Now, depending on how you want to look at this, oxygen is one of, if not the most abundant element on Earth. Not necessarily in our crust, but there is a huge amount of oxygen in one particular place on our planet, and that's in the oceans, because it's made up of 2 parts hydrogen, 1 part oxygen. And there's a massive amount of oxygen on our planet, okay? The air we breathe is only made up of about 19% oxygen. So every time you take in a deep breath of air, you've got about 79% nitrogen and about 19% oxygen. So while our body doesn't use the nitrogen, we just exhale it right back out. But you take in, you use about 9 to 10% of that oxygen that you take in. Okay, so we thrive on oxygen, obviously, and while it is bad that we are polluting, there is still an abundancy of oxygen left on our planet. Okay, but it is considered one of, if not the most abundant element on our planet. Okay, let's see. Next group are going to be the halogens, or also referred to as the halides. This is group 17. These, just like group 1, are very reactive. And just like group 1 and group 17, they are so reactive that you don't find them by themselves in nature. They almost always have to be paired with something else. In the case of the halogens, that sometimes means that they're paired with themselves. But one of the things about the halogens is they are very toxic, and with fluorine being one of the most toxic elements on the planet, chlorine gas is one of the primary ingredients in mustard gas. It is a green toxic gas, and if you've ever heard the warning of do not mix bleach and ammonia cleaners together, it's because you can inadvertently make chlorine gas and you can burn your lungs. So it's a very, very toxic gas, and can cause lots and lots of harm to your lungs. Okay, so don't mix chlorine and ammonia. The last column we'll talk about, called the noble gases. Hopefully you've heard of these before. The noble gases are called such because they are complete. They're filled with the amount of electrons that they need to be satisfied. And so because they're filled, they don't actually combine with anybody else. They are royalty. They don't like the other pion elements. They are insignificant. But they are so isolated that actually for the longest time we didn't even know that the noble gases existed, because they don't react with anything. It was hard for them to be discovered, and it wasn't until somebody did a very simple test of figuring out what's in air to find out 79% nitrogen and 19% oxygen, and there were all these little tiny other trace gases, and then there was 1% of the air made up all of the atmosphere, but it didn't react with anything. And finally someone realized that it was a completely new element, and it was argon. So our atmosphere actually has 1% argon in it. Once we realized that there was a whole nother column, then the others started falling into place. But they are very stable, and mostly gases. Okay, so a couple of other ones that I did not talk about. First one being hydrogen. Hydrogen, it's in group 1, but hydrogen is not a metal, it's a gas. Okay, and it's in group 1, and it has 1 proton, and that's why it's located in that one space on the periodic table. But it is very reactive. It will not be by itself, and if that means it's paired with itself, paired with another hydrogen atom, that's okay. But you will not find a single hydrogen atom by itself in nature. It will be paired with something. Okay, and most of them are usually paired with oxygen or carbon. So not saying that they can't pair with other things, but the majority on the earth are paired with hydrogen, or paired with oxygen and carbon. Okay, The last two things to talk about are at the bottom of the periodic table. The lanthanides and the actinides. Okay, the lanthanides, they're row 57 to 71. They're rare earth elements. And upon their discovery, it was really hard to find a place for them to fit somewhere in the periodic table. And with lots of research and lots of work, it was discovered that actually they were, well, I moved that picture. They're actually that one other little section of the periodic table that fits in right here, okay? When the actinides, numbers 89 through 103, most are radioactive. And everything on the periodic table after uranium, everything after 92 is synthetic. They're man-made. So all these outlined ones here, some of them only occur for a split second in a particle accelerator. They are very unstable, they are very reactive, and we have not found them in a stable place on Earth anywhere. They are all man-made. Okay. Overall, those are the main things about the periodic table I wanted to talk to you about today. Next class, we're going to continue our talk with atomic structure. So I'll see you next time. Remember, work together, help each other, and make the world a better place. See ya.